Well, today we're going to talk about gravitational force. We've already used the idea of gravitational force in free body diagrams. We've talked about gravitational acceleration, so we're going to start out with a little review. One thing we know is that objects are accelerated towards the center of the Earth with this acceleration. It's always the same near the surface of the Earth. That's called g. It's equal to 9.80 meters per square second. But the other thing we know is from Newton's first law, we know that objects don't get accelerated unless there's a force acting on them. So we know that there's got to be, in addition to an acceleration due to gravity, there must be some force due to gravity that causes this acceleration. Another thing that we know from Newton's second law, which remember says F equals ma, we also know that the force that's on that object is proportional to whatever its mass is. And another thing that we know from Newton's third law is that for every force there's an equal and opposite force. So the force that's exerted on the falling object that causes it to fall, well, that object must also be exerting an equivalent force on the Earth. And the force that causes has got to be equal to the mass times g, which is the acceleration due to gravity. That force has got to be acted on both ways. It turns out that this invisible or non-contact force that we call gravitational force exists not just between the Earth and other objects, or between huge objects like the Earth and the Sun, but it exists between any two objects that have mass. Here are the rules. The gravitational force is directly proportional to the masses of the objects. We don't know exactly why this is true, but we do know that it's true. The heavier they are, the bigger that force is going to be. We also know that it's inversely proportional to the square of the distance between the centers of the object's masses. So as the objects get farther and farther apart, the force due to gravity that pulls them together is going to get lower and lower. So if we quantify this, we put this in terms of an equation. Here's how we can say this. They've actually experimentally determined what this g is, and that number is, that's a constant of proportionality, 6.67 times 10 to the negative 11th, very small number, Newton meters squared per kilogram squared. That multiplied by the mass of one of the objects times the mass of the other object, divided by the square of the distance between the two objects, that's what d means here, that's going to be the force due to gravity between those two objects. Let's do some problems. Here's one. What's the force between Wally, who has a mass of 120 kilograms, and Tony, who has a mass of 64 kilograms, if they're standing 3.201 feet from each other? Let's switch to a different format to solve this problem. One of the things that you'll notice as you start doing these kinds of problems is that we almost always need distance to be in meters, we almost always need mass to be in kilograms, and we almost always need time to be in seconds in order to make all the standard units work out. So it's probably a fairly good practice shortly into the problem to look for masses, change them into kilograms, look for distances, make them meters, look for times, and make them seconds. So let's start out here. It says that Tony and Wally are 3.201 feet from each other. Well, let's change 3.201 feet into meters. So we'll use dimensional analysis. We know that there are 12 inches in a foot. We know that gets us into inches. There are 2.54 centimeters in an inch, so that's going to change our distance to centimeters, but we want it in meters, so we'll use this fact. 100 centimeters is the same thing as 1 meter to get us into meters. Cancel centimeters up. So when I do this conversion, here's what I find out. This distance, 3.201 feet, is 0.976 meters, just shy of a meter. Okay, now let's take that and put that into the equation for gravitational force. The force due to gravity, remember, is g times the mass of the first object, which is going to be Wally, let's say, times the mass of the second object, which will be Tony, divided by the square of the distance between Wally and Tony. Let's plug in some numbers. G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Wally's mass was 120 kilograms. Tony's mass was 64 kilograms. And we've just determined that the distance between them in meters is 0.976 meters, and that's going to be squared according to our equation. Okay, look at what happens to the units. I'm going to have square meters down here, so my length unit is going to go away. I'm going to have kilograms on the bottom squared, but I'm going to have kilograms times kilograms on the top, so that unit is also going to go away. And the unit that I'm left with, the only uncanceled unit, is newtons. And that's good, because what I'm looking for here is a force. Now, if I grab my calculator and do this calculation, here's what I find out. The force between them is very small, 5.38 times 10 to the negative 7th newtons. So it's about 5/10 millionths of a newton of force, which is why two ordinary guys would not get stuck together due to gravitational force. Well, here's another one. What's the force between the sun, which has a mass of 1.99 times 10 to the 30th kilograms, and the Earth, which is 5.96 times 10 to the 24th kilograms? The Earth, 6 orders of magnitude, which is about 1,000,000 times less massive than the sun. And then here's more information. The Earth's orbit, which would be the distance between the two bodies, is 300 million kilometers. Well, let's go through that conversion to meters thing first before we do anything. 300 million is 300 times 10 to the 6th, and that's in kilometers. And we're going to want that converted into meters because that's what makes our units all work out. Here's what we know. There are 1,000 meters in a kilometer. So 1,000, we can think of that also as 10 to the third. When we do this multiplication, we're going to end up with units of meters, which is what we want. So just adding the exponents together, we find out that it's 300 times 10 to the 9th meters. Now let's switch to a different format and plug that information into our problem. So the force of gravity between these two bodies in our solar system is going to be Fg equal to, again, g times the mass of one object, we'll call that the Earth, times the mass of the second object, the Sun, divided by the square of the distance between the two of them, which is the radius of Earth orbit. So we'll plug information in here with numbers and units. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. That's going to be multiplied by mass of the Earth, which was 5.96 times 10 to the 24th kilograms, times the mass of the Sun, and the mass of the Sun was 1.99 times 10 to the 30th kilograms, and then that's all divided by the square of the distance between the two, which we just found was 300 times 10 to the 9th meters. So we square that number. The units will work out just like they did for the last example problem to be units of force, which are newtons. When you do the calculation, you find out that this is a much bigger number, 8.8 times 10 to the 21, many orders of magnitude larger than the force between the two guys, Wally and Tony. Well, you'd expect that, and that's what holds our planet in orbit, is this giant force. This problem is asking us to find the force between J, who has a mass of 75 kilograms, and the Earth, which has a mass of 5.96 times 10 to the 24th kilograms. And we're to assume that J is at the surface of the Earth, which has a radius of 6.37 times 10 to the 6th meters. Well, everything is in the units that we want, so let's just plug this into the equation and find out what our answer is. Do it right here. The force due to gravity is G again, 6.67 times 10 to the negative 11th Newton meters squared per second squared, multiplied by the mass of J, which was 75 kilograms, multiplied by the mass of the Earth, 5.96 times 10 to the 24th kilograms, it was in the last problem, divided by the square of the distance between them. Well, the distance between J and the center of the Earth is the radius of the Earth, which is 6.37 times 10 to the 6th meters, assuming J is sitting at the center of the Earth, and that's squared. So this will come out to be units of newtons. We find that this answer is 735 newtons, and that's somewhere in between the very tiny force between the two guys, Wally and Tony, and the very gigantic force that was between the two planets, the Sun and the Earth. This problem wants us to use the answer to the last question, which remember was 735 newtons. It wants us to use that to find the acceleration due to gravity. Well, we know what the acceleration due to gravity is, but we're just going to verify it here. Remember that F equals ma, so force due to weight, which is what this is, 735 newtons, is equal to m times g. So g would then be the force due to weight divided by the mass. So 735 newtons was the force that J caused on the center of the Earth, and his mass, remember, was 75 kilograms. Well, in terms of units, this could be written 735 kilogram meters per second squared, because that's what a Newton is, divided by 75 kilograms. Well, with the kilograms canceled out here, we get nice units of acceleration, meters per square second. And when you divide 735 by 75, you'd expect a number about equal to 10, and in fact it's 9.8 meters per second squared.